Okay, good morning everyone. Let's get started. A couple of housekeeping items before we get back to lecture. Just a reminder, I usually videotape all the lectures and put them up on YouTube after class. I don't know what I did last time, something got messed up. So I mounted last year's first class to our schedule. I'm running the course this year the same way that I did last year. So if you want to go back and you have any questions about the logistics for the course, go back and watch the video lecture. It's all in there. Everything should be clear. On the subject of logistics, any questions about anything we talked about last time? We're all good? Okay, just a reminder, you're working on assignment 1, which is the main hurdle in assignment 1 is getting PyroSim installed up and running to the point where you get an empty physics engine running. How many people have got that far so far? Some of you yes, some of you no. Okay. If you need a USB drive from me, if you're a Windows user and you did not get a USB drive from me from last time, come up to me, see me at the end of class, and I have some more here for those that don't have one yet. Okay, any other questions? You're going to be submitting all of your solutions, as I talked about last time, into our subreddit here, Ludobots. We have some online students that are taking this course alongside all of you. Someone asked about a chat room last time. Last time I checked on Reddit, there were no chat rooms, but I figured out how to add one. So if you go to our subreddit, you'll see in the top right there, the little talk bubble. You can click on there and there's a chat room. Knock yourselves out. Again, as I mentioned last time, peer assessment is a great way to test your own knowledge of the course material. Best way to learn something is learn it and then try and teach it to someone else. So do feel free to ask questions and help others as best you can in the chat room and in the subreddit. Any questions about that? Yes?
Is there a standardized format you want us to use in our post titles?
Usually there is a standardized format, and someone has it there. There's one that's correct. So we're looking for things that have a tag in front, a submission. There's an automated way. If you click on the submission arrow at the end of every assignment, it should copy and paste that standard template in there for you. I see some people shaking their heads. It used to. Okay. You can type it in manually if you want. It doesn't matter. What matters for you guys is that you make sure to get the URL submitted to Blackboard. It doesn't really matter about the standardized title. Obviously, Reddit is changing as we go, so I guess we lost that functionality somewhere along the lines. Doesn't matter too much. Yes, sir?
You say you make a single post at one point to wherever your favorite Imgur or whatever.
Yep.
I made an album and put a bunch of pictures in that. Is there a way to do multi-images as a single post other than an album?
I'm sure there is. I don't know how.
Okay.
If somebody figures it out, go drop it in the chat room and explain it to others. Exactly. Any other questions? No? Okay. Again, for those of you that haven't tackled assignment 1 yet, please do so as soon as possible so that we can iron out all the installation issues and then we're all on the same page. We all have an empty canvas, an empty physics engine, and we can move on to the more interesting parts of the assignments. Okay, so in these first 3 lectures, we're going to just sort of go over what are robots, what is AI, what's the difference between the two. We'll have a look at the history of AI today. It's a vast field, AI, obviously, and we're going to try and situate evolutionary robotics, which for the next 14 weeks is going to be our particular approach to trying to understand and instantiate intelligence in machines. And we'll probably start on lecture 3 today, which is coming at evolutionary robotics from a philosophical point of view, embodied cognition. The basic idea of embodied cognition is if we want to understand thinking, we can't just look at the brain. The brain sits inside of a body. We use our bodies to push against the world and observe how the world pushes back. And that feedback loop becomes the raw material for us to learn about what we can and can't do in this world and becomes the platform on which intelligence is built. That's the idea of embodied cognition. We'll probably start on that today. Okay, however, we did not finish lecture 1 last time, so let's jump back to lecture 1. We finished last time by talking about the assignments, and I gave you sort of 4 ideas here, just to start to get you thinking about what you might want to do in the last 4 weeks of the semester, some sort of sample final projects, and I put some links in there to student projects from years in the past. As in the assignments, in the final project, you're going to be submitting all of your material as a video to YouTube. So if you go to YouTube and you type in CS206 final, you'll see dozens of videos from previous years, and you can see pretty much all the final projects from years past. Okay. All right. Robots. Why robots? We're going to spend most of this course talking about the how of robots. How do we go about evolving robots to perform useful or interesting tasks? Before we tackle the how, however, let's talk a little bit about why we might want to go about building robots. The first reason, of course, is they're awesome and interesting and cool. Everybody wants to build robots, right? That's a good reason. There are lots of other reasons, and I hope you find your own reasons throughout this course. One of them is a very practical economic engineering reasons, which is robots at a base level are simply machines, and humans have been building machines for thousands of years, and robots are just the latest kind of machine that we figured out how to build. Robots, like all machines, help humans do things easier, faster, at scale, and so on, right? We already have robots. So if you look at the top pair of images, industrial robots were introduced in the 70s and 80s, and they allow us to build things indoors faster, more cost-effective, and at scale. The picture in the top left is from one of Henry Ford's very first factories. Right? It may not look like a factory because we're sort of used to the picture in the top right there, but it is a factory in the sense of it's a constrained environment in which we have a number of workers. In this case, they're human workers. Each worker has a specialized task, and they're carrying out that specialized task on an object that's being constructed. In this case, it's motorcycles. So Henry Ford came up with the idea of mass production. Henry Ford invented sort of the horseless carriage or automobiles. But more importantly, Ford invented the way that we build automobiles and now build pretty much everything else. And the idea there was to systematize things. We have a large number of workers that are doing one thing and doing one thing well. So that systemization over 100 years ago led the way many decades later in the 1970s to automation. We replaced the human workers in many cases with robot workers. There was a lot of discussion in the 1970s about robots coming for our jobs, which they did in the case of industrial and blue-collar jobs. That discussion sort of faded out for a while, and now that discussion has come back with a vengeance because now the robots are out not just for blue-collar jobs, but for white-collar jobs. We'll spend some time towards the end of the course talking about the ethics of robotics. Should we go about building robots? How much of our society should we automate, and how should we go about doing that? It's already happened once in terms of the way that we build things indoors. The bottom pair of images shows a historical snapshot of the way in which we build things out of doors. How does the bottom pair of images differ from the top pair of images?
Construction is still done by people.
Construction is still done by people. That was a picture from somewhere on campus about 10 years ago. You can go look at a construction site at the moment. You'll see mostly people. You'll also see some machines like earth movers and so on, but inside that machine is usually a person driving the machine, so it's a non-autonomous machine, right? The industrial robots in the top right are autonomous. They're making their own decisions about what they do. If robots are such useful tools for speeding up the way that we build things indoors, why haven't we roboticized the way that we build things out of doors?
The environment's really irregular.
The environment is very irregular. Imagine we had a simple robot and all we wanted it to do was sort of clean up the construction site overnight when the workers went home, and we wanted the robot to simply move bricks from pile A to pile B. And we left the robot to figure out how to do that. A robot might decide to pick up bricks at point A and throw them to point B. Perfectly fine, as long as there's nobody around. There may be a road between point A and point B, so the robot picks up some bricks and starts to cross the road. At another construction site, it may be raining. Point A and point B may be in different positions, in different locations, under different conditions at any different location. So every single construction site is going to be different. The whole point of a factory is to remove all of those individual differences and create a clean, unobstructed environment so that the industrial robots can do exactly the same thing over and over again. If we want robots to help us out here in the real world, they're going to have to constantly adapt the way that they carry out the desired task for every change in the environment. And getting a machine to do that is still an open problem. We haven't figured that out. We haven't figured that out yet. The Greek philosopher Heraclitus over 2,000 years ago said, "Man never enters the same river twice." Humans always are adapting to change. Some of you may have taken a class in this room before, but even if you haven't, you kind of know how things work. It's a different room, you find a chair, you sit down, you open your book, and off we go. We are constantly adapting to the world around us, and it is so easy for us, we forget that trying to get a machine to do it is extremely difficult. So what we're going to spend most of the time in this class doing is creating not just autonomous machines, we already have that, industrial robots, that's relatively easy, but creating machines that are both autonomous and adaptive. That is extremely difficult to do, and no one has a good answer for how to do that yet. Okay, so that's sort of an engineering or economic answer to why we might want to go about creating machines. If we could build things out of doors, it would become much more cost effective to fix bridges, create new infrastructure, and so on. There are other reasons why you might want to study or build robots. And here's a reason which is more scientific or philosophical than it is engineering. If you look at a lot of the different branches of science, a lot of them are sort of not necessarily solved, but we have a lot of the big pieces in place. So in the case of biology, if you want to understand anything in biology, there is an underlying principle that if it doesn't at least explain that phenomenon, at least will get you started on the path to understanding that phenomenon, and that's Darwinian selection or evolution. Right? Physics has Newtonian and quantum mechanics. There's a guiding principle in chemistry. What is it? Chemistry isn't just sort of a collection of random observations. There is something that structures all scientific inquiry in chemistry.
Conservation of mass.
Conservation of mass, that's important. We might put that one in physics. If you remember back to your high school chemistry class, what is the thing you spent most of the time staring at? Atoms.
Periodic table.
The periodic table, right? So it turns out that in terms of chemical substances, there seems to be some underlying structure, and we've sort of figured that out. There's still obviously a lot of interesting questions in chemistry, but some of the big guiding principles are already nailed down. In the study of intelligence, there is no guiding principle yet. There are open questions about how organisms evolve, acquire, and exhibit intelligence. And proof that we haven't found the guiding principles yet is we haven't created intelligent machines that are anywhere near as intelligent as the simplest organisms. We're at the very beginning of the beginning of the beginning of studying intelligence, understanding it, and building it into machines. Several Nobel Prizes waiting to be won in this field. Maybe one of you will find your way to win one. Okay, another appealing aspect of robotics or evolutionary robotics is that it's an extremely interdisciplinary study. We're teaching this class in computer science. It could equally be taught in engineering, philosophy, psychology, the biology department, the math department. Lots of places where the study of robotics could originate. As we'll go through this course, and as I've already mentioned, this is going to be a very broad course. We're going to touch on lots of different concepts from lots of different fields. I already introduced you to a concept from evolutionary biology last time, exaptation. We had a robot that was adapting to pick up the block, and then gradually evolution adapted that behavior into something else, which was walking. We saw another idea from AI, which is perverse instantiation. The robot got the block onto its back, but maybe not in the way we wanted it to. So we're already starting to see different concepts from different fields. As we go through this course, we're going to touch on all these different topics. We're going to look at philosophy of mind. When we say a human is intelligent, what do we actually mean by that? We'll clearly see some math, some chemistry. We're going to look at soft robots. This is 3D printing very exotic materials out of lots of different chemical substances to have a soft robot that walks out of a 3D printer. Obviously, all of the different branches of engineering come to bear here: mechanical engineering, electrical engineering, bioengineering. We're not going to be building any physical robots in this class, but we will talk about some of them. Obviously, computer science, we're going to do a lot of coding here. Physics, you're going to be working with a physics engine. So if you've forgotten force equals mass times acceleration and other aspects of your high school physics, you will be reminded of them shortly. Biomechanics, so the science of movement. As I mentioned last time, movement and intelligence are ultimately linked. We'll spend a fair bit of time talking about biomechanics, psychology, cognitive science, neuroscience. All the different disciplines of the mind and the brain are going to be important for us. And of course, evolutionary biology. Okay. So there's some intellectual reasons why we might want to study and try and create robots. Back to the engineering for a moment. There are some very real practical reasons why we might want to create robots. Obviously, as a global society, we're facing some serious energy challenges. There's lots of new solutions that are out there. A lot of them have been deployed. If you look at a lot of the green energy solutions that are being proposed or implemented, they have one thing in common, which is they are all some kind of a farm. We have some element which might be a turbine or a solar panel or these wave worms, if you like, and we need to create large numbers of them, spread them over a very large area, and only then, through the economics of scale, might these green energy alternatives be able to compete with oil and gas and so on. If you deploy infrastructure at this scale, there are a number of challenges that arise. What are some of them? Maintenance. So, do we send a human worker out and up a turbine to fix it? Do we send a robot out and up a turbine to fix it? Do we send a drone that doesn't have to climb the turbine to go fix it? Do we instead consider the turbine as a robot itself? Maybe we build some intelligence into the turbine so that it can adapt to changing conditions and maybe minimize the amount of maintenance we have to do over time. What's starting to become obvious with the deployment of these very large-scale green energy farms is that robotics and AI are going to be a necessary component of these systems. How and in what way, again, is an open question. Okay, so why evolutionary robotics? I've tried to give you some reasons about why we might want to study robots. Why take this evolutionary approach to robotics? So as I mentioned last time, in evolutionary robotics, we're not going to be programming the robot by hand. We're going to be creating an evolutionary algorithm. That evolutionary algorithm is going to create a population of robots. The computer is going to measure the performance of every individual robot in the population. Those individuals that score low according to the computer are deleted. The survivors produce randomly modified copies of themselves. A very boiled down, simplified version of Darwinian selection. We're going to put that in a computer. That's evolutionary robotics. Why take that approach to robotics rather than others? One reason, one of the most obvious ones, is that it's very difficult, again, to program robots by hand. I told you that last time. Here's an example. The little animated cartoon that you see in the top right, this is known as a Stewart platform. This comes from mechanical engineering. It has a number of interesting properties. As you can see in the cartoon here, we have these two circular plates, and these two plates are attached to each other with 6 linear actuators or pistons. And you can see what pistons do. They obviously extend or contract. As they do, they can rotate the upper plate relative to the bottom plate. So far, so good? Okay. Let's say I take one of these Stewart platforms, put it on its side, take a second one, glue them together, and put 1, 2, 3, 4, 5, 6, 7, 8, 9 rods on it. And we then have what came to be known as the nonaped robot, the 9-legged robot. This is a project that I helped out with at Cornell. So we have 2 of these Stewart platforms together. Each Stewart platform is made up of 6 pistons, so we have a total of 12 pistons inside the nonaped. Let's, as a thought experiment, try and create a controller for the nonaped by hand. And the way we're going to do this is to create a very, very simple controller. Instead of creating a neural network, we're just going to create a matrix. We'll assume this matrix has 12 rows, 1 row for each of the 12 pistons, and then let's say we have 1,000 columns, where each column represents the 12 commands we're going to send to the 12 pistons. So far, so good? We'll assume, for simplicity's sake, that this is a binary matrix. A value of +1 means for that motor, or that piston, we're going to send that particular signal at that time. +1 means extend the piston, -1 means compress the piston. All good? Here's our nonaped down here. Let's assume this is the front and this is the back, and we want the nonaped to move forward as quickly as possible. Go.
How many time steps does it take to fully extend the piston?
We'll assume that these are extremely strong pistons, which they are. Obviously, I'm going to play the video for you in a moment, but I don't want to give it away. Let's assume that they will extend immediately. When you send +1, they will be fully extended when you go to the next time step. Let's assume for the moment that each time step is about ½ a second. Doesn't really matter for our purposes. Okay. Might be hard, especially at 8:30 in the morning, to dream up a matrix that will get this robot to work. What are some general strategies that may work here? Yes?
You could extend the pistons on one side, so one side elongates, and then do so on the other, and kind of like shimmy almost forward.
Possibly. If you look at the cartoon in the top again, it turns out that it's actually hard to get the top plate, in this case, to move straight out. If it moves straight out, it also twists, right? So we can't necessarily control the relative position of the plates independently. If we try and extend, it also twists. If we try and compress, it also twists. If we want to twist in a particular direction, it also extends or contracts. Tricky. Clearly, I chose this example because this one is particularly tricky.
You could maybe compress all of the legs and then quickly extend the back ones to leap it forward, then extend them all to catch it, compress, leap.
That might work. We might be able to compress all of the front 6, for example, and that might cause it to lean back and then maybe jump forward. Maybe, maybe not. We'd probably have to try it, right? We try it, it works, maybe it doesn't work. If it doesn't work, we try something else. How many trials do you think we might have to do until we start to get significant forward motion?
Hundreds.
Hundreds. I can promise you it's actually thousands. So I mentioned this was a project we carried out at Cornell. I'll play the video for you in a moment. You can see we put it inside this wooden cage. There were no humans inside this cage. This robot is pretty strong. You don't really want to be near it when it starts moving. We had a computer attached to it by a cable, which you can't see here. And the computer, again, was coming up with one of these matrices after another. It started by creating a random matrix. We sent that to the robot. The robot did its thing for about 30 seconds. There's a winch that pulls that robot towards the back of the cage. We then hit another button. The computer sends a second matrix, a third, a fourth, a fifth. There were two of us working on this. My job was to sit there and press the enter key every 30 seconds. It was extremely exciting. We stayed there for 14 hours and eventually got something that moved relatively quickly, but it took thousands of trials to do so. These are some random controllers. You get motion, but not necessarily coordinated motion. Here was us just trying out a few basic movements. You get the nonaped to dance. That was relatively easy. We could program by hand some of these simple behaviors. This one was actually discovered by evolution. We could create some simple ones that got the robot to move slowly, but to get it to move really quickly, we ran out of ideas and we needed this evolutionary process to try things out. Okay, of all those gates that you just saw, is that the fastest that the nonaped can travel?
I was just wondering if
Yep.
it ever used the 3 legs on top.
Well, okay, so why the 3 legs on top? If this robot is moving downhill or flips over or falls on its side, it can carry on, right? So they're just sort of there in reserve. As I mentioned, this robot has 12 pistons, so there are 12 rows in this matrix. Let's assume that we're going to send 1,000 half-second commands to the robot. So we have a 12 by 1,000 binary matrix. How many controllers are there? How many ways are there for the nonaped to move, given this way of controlling it?
12,000?
Not 12,000, a lot more than that.
2 to the 12,000?
2 to the 12,000, right? We have 12,000 elements in this binary matrix. Every element can be -1 or +1. We have 2 to the 12,000. If it takes 30 seconds to try out one matrix after the other, how long would it take for us to try out every controller? All right, I'll leave that for you to think about. It's much longer than 14 hours. Do you have an answer? Okay, question.
So why do you guys choose balls as the place of contact?
Okay, so those are rubber balls because we were using carbon fiber for the legs. That black material is carbon fiber, which is relatively rigid. You can see that this robot is pretty strong. Without the balls, it would smash itself to pieces in about an hour. So it's just to absorb contact. And
Why don't you have like a foot kind of thing, just to make it more like evolutionary or something?
we could have made it more biologically inspired. We could have put feet. We could have put a lot more things on there. We were just trying to keep things relatively simple in this case. So in all the evolutionary robotics experiments you're going to see in this course, including this one, there are, to all intents and purposes, an infinite number of potential solutions. In this case, there's 2 to the 12,000. There isn't enough time until the heat death of the universe to try out all solutions one after the other. So instead, like evolution, we're going to try and move through the space of potentially infinite solutions and try as best we can in a limited period of time, in this case 14 hours, to find the best solution we can given that 14-hour budget. In most cases, we can find something that works pretty well, again, like you saw in the video here, but there is one severe cost that we incur in this particular approach, which is that we can never guarantee that we found the best one. As far as anybody knows, the only way to guarantee that you found the best one is to try them all, right? Okay. That may not necessarily be the case. Again, as I mentioned, this is an open field. So how well you can do given less than the time until the end of the universe is an open question. Okay. So we're going to have to use some process to search for robots for us, search for controllers. There are many learning approaches out there that can tune these controllers, that can also search for controllers. One of the main things that distinguishes evolution from learning, which I mentioned last time, is that evolution does not just tinker with the brains of organisms, it sculpts brain and body simultaneously. So in many of the evolutionary robotics experiments you're going to see in this class, especially in simulation, you're going to see an evolutionary algorithm that is changing not just the brain of the robot, but the body as well. This is, again, a snapshot from an evolutionary process. This is an experiment I worked on years ago. You'll notice evolution discovering a lot of solutions that don't work very well here. Here's a relatively complex one. The grayscale of the spheres, the black and white spheres, just indicate that there's a neural network in there or not. So black spheres have no brain material in them. White spheres, there's some brain material in there. Here's a bilaterally symmetric robot. It's the same on the left as it is on the right. Doesn't go anywhere, so it gets low fitness and is deleted. This robot is deleted, and this strange sort of horse and rider one that you see here, for whatever reason, seems to work. It is not bilaterally symmetric. The left side of the body does not look like the right side of the body, which is kind of interesting. Most organisms on Earth that move are bilaterally symmetric. Maybe given more time, evolution would sculpt this into something that's more symmetric. Maybe not. As this video shows, evolution often discovers somewhat surprising solutions, but if they work, they work. Okay. Why would we want to try and evolve the body along with the brain? We have lots of examples in nature of body plans that seem to work very well. There are good body plans for moving over ground. There are a lot of interesting flying organisms that demonstrate body plans for flying and swimming and jumping and burrowing and so on. Why not just borrow a body plan from nature and program a controller into it?
Exact same controller that the animal has.
Exactly. So obviously brains and bodies in nature are evolved to work very well together. If you look at the airplanes in the sky, they're not giant flapping birds. They look actually quite different from birds, and there are good reasons for that. We'll talk about that later in the course when we come to talking about evolving bodies and brains. Okay. As I mentioned, learning algorithms only optimize controllers, so we're going to talk about the history of AI in a moment, but here's my very short version of the history of AI. Since about the 1940s, people have been trying to create these things called neural networks, where neural networks are made up of neurons, the circles that you see here, or synapses, which are connections between neurons. Since about the 1980s, people have been trying to figure out how to gradually tune the weight or strength of these connections. By changing the strength of these connections, you change the transformation of signals that are arriving at the input layer here to the output layer here. As I mentioned last time, you can think of neural networks as a function that transforms input into output. If you tune these synapses, you change the transformation function. Figuring out a way to do this efficiently so that you finally get something that works has taken 30, 40 years for us to figure out. The best solution was posted in the literature about 12 years ago now, and that was the beginning of the AI revolution and paved the way for everything that's happened since. It took us about 30 or 40 years to figure out how to tune these synapses. What about the structure of the neural network? Why 6 neurons? Why not 7? Finding the structure of a neural network for, in our case, a robot, is an open question. Nobody knows how to do that well. What about finding the body of the robot itself? Let's say we have a wheeled robot or a legged robot. We have some task we want the robot to perform. Are wheels better or are legs better? Perhaps if we choose wheels, it'll be easier for evolution to tune the neural network to get the robot to do what we want. Or maybe if we have legs, it'll be easier for evolution to tune the neural network to do what we want. Who knows? Again, these are open questions. So in the history of AI, we figured out how to do this well. We don't know how to do this well, and we don't know how to do this well. Another reason why it's a good idea to use evolution. Third reason is we have an existence proof. If we want to try and create machines that have animal or maybe human levels of intelligence, we know of one person who's done it. It's taken her 3.8 billion years to figure out how to do it, but it's possible, right? Evolution can produce autonomous and adaptive machines. So in this course, we're not going to borrow or steal ideas from any one organism. Instead, we're going to steal ideas from the algorithm that produced the organisms. Right? There is a sister field to evolutionary robotics called bio-inspired robotics, which is you pick an organism like a human or a dog, you build it in metal, and then try and get it to do what you want it to do. In bio-inspired robotics, they're trying to instantiate a product of evolution, a particular organism. In evolutionary robotics, we're trying to instantiate the process of evolution. By doing so, our artificial evolution sometimes gives us back something that's recognizable. It looks like something we see in nature, sometimes not. The last reason that we're going to look at evolution here is we're going to usually be working with a process in which there's no supervision. And what do I mean by supervision? If you study machine learning, you'll very quickly learn that there are sort of two classes of AI methods: supervised learning and unsupervised learning. In supervised learning, let's assume, for example, again, we have our controller down here. In this case, we have this simulated biped in the bottom right. We take one controller and we drop it into our biped, and the biped robot does this. Takes about 12 steps and then falls over. We know that there are controllers that produce robust bilateral bipedal walking. That's us. We do it. So we know there's probably a controller that's better than the one that you just saw. In supervised learning, there is an algorithm that would, in theory, be able to say, there's the problem. That should have been a +1 rather than a -1. That's supervised learning. In robotics, we typically don't have that case. All we have is a robot, and that robot works or doesn't work, and we just get back a single number. It's basically a number that says the robot traveled 1.8 meters forward. So the number we get back is 1.8. We take that number. Where's the problem? Where do we make a change in the robot's controller to make it travel further than 1.8? We don't know. We don't have any supervision. So a lot of the supervised learning methods that are out there that are very successful in other domains, like recognizing objects and images, does not exist or is not applicable for robotics. So here are 4 reasons, and we'll see many more as we go, for why we might want to take an evolutionary approach to trying to create robots. So far, so good? Okay. Just to finish off this lecture, this is an interesting video from a few years back now. Another evolutionary approach, a little bit more up to date. As you'll notice at the beginning here, they're evolving not just the controller, but the placement of the pistons. And the pistons are going to pull on different body parts. The evolutionary algorithm that you used here is clearly adaptive because it can adapt solutions to different kinds of body plans. Very different body plans. You'll notice this one is using its tail. This is a nice video because you can sort of visualize the evolutionary process itself. Remember, for every generation, there's a population. They're showing the best individual from every generation, or from some generations. Notice these two methods of locomotion. Obviously, one is better than the other. One is more efficient than the other. You can see it, right? Okay. It's a fun video to watch. As you can imagine, when this was posted to YouTube, it was very popular. Go watch the rest of this video. Okay, so let's move on now to our history of AI here. We're going to do this again chronologically. Again, the field of AI is vast. We could spend a whole course on this. We're going to do this in about 75 minutes. We're going to go back. We're going to start our journey in the 1600s with cogito ergo sum. Who said that? Descartes. So we're going to start with Descartes. He actually says, je pense donc je suis. He wrote in French because he wanted to reach out to the common man and the common woman and didn't want to be uppity by writing in Latin. Okay, not so important for our discussion today. Why are we talking about a French 17th century philosopher in an evolutionary robotics class? Seems like a strange place to start. Descartes is justifiably famous for some very deep thinking, so this is an injustice to his thought process, but I'm going to try and boil this down for our purposes. I think, therefore, I am. This is his conclusion that comes about from the following thought experiment. Descartes sat down and wanted to decide or prove once and for all what is knowable and what is not. There's certain things that we think are true. I think I see about 50 of you out there. But we all know that our eyes can deceive us from time to time. If you've seen the Matrix movies, you also know that machines can deceive us from time to time. I can't really, and Descartes could not really, trust his senses. So if you can't trust what you see, hear, taste, touch, and so on, it starts to get a little worrying. Unless you're deeply religious, which Descartes was, it's kind of hard to be clear about what is real. What can you really believe in that you know objectively exists? So he started by asking, well, do I exist? I don't know about all of you. I don't know about all of the objects I see out there, but maybe I exist, because the I is something that I sense without seeing it or hearing it or tasting it or touching it. But how do I even know that I exist? That's also kind of tricky. However, this thing that I'm referring to with this pronoun I, it's that thing, whatever it is, and I'm not quite sure what it is, but it's the thing that's asking the question, do I exist? So the thing that's asking the question exists. I'm not sure what it is, but I'm pretty sure it exists. Everything else, I'm not so sure of. Again, Descartes was religious, so for him the I was a soul. Today we might say the mind. There is something in here that is asking the question, that is looking out through the eyes of the body onto the environment. None of those things, from Descartes' point of view, may have been trustworthy, but the thing that was looking out or asking the question, the I, is knowable, is real. So that set up a very important distinction. These are two very different things. The res cogitans, the I, the soul, or the mind, is one thing, and the body is something else. In the centuries to follow, this has become known as Cartesian dualism. There is a distinction between these two things, and you're going to see throughout this course that this idea of Cartesian dualism crops up over and over again, and it has deeply influenced the way that we go about trying to build intelligent machines. I've already shown you one way in which Cartesian dualism has influenced the way we've done AI in the last 50 years. What was it?
Evolving the mind and body separately.
Exactly. If you look at most robotics work outside of evolutionary robotics or AI, the focus, as we just saw, is on the brain, trying to tune the synapses inside a neural network, and we'll assume everything else is sort of fixed or is easy. The hard part is the mind, the soul, the neural network, the thing inside. It already, Cartesian dualism greatly influences the way we go about trying to build intelligent machines. What most evolutionary roboticists try and do is militate against dualism. We're going to try our best to blur the distinction between the brain of the robot and the body of the robot. Clearly, from evolution's point of view, these are just two tightly interlocking subsystems, and she sculpts both subsystems simultaneously. Why would we go about fixing one and trying to tune the other? Doesn't really make sense if you think about it. Part of the reason why is Cartesian dualist thinking. Okay, as I mentioned last time, you'll see a bunch of red boxes throughout the lecture slides. That's just a prompt to you to either annotate the slides or take notes as we go. As I mentioned, we're starting in the 1600s here. If you're interested in this argument here that Descartes made, again, I'm not doing it justice here. Go back and have a look at Discourse on Method. Definitely required reading for anyone interested in cognition and intelligence. Okay, let's jump 400 years into the future to 1936. And any CS course usually starts with Alan Turing. Alan Turing made this thought experiment about this hypothetical machine called a Turing machine. Every single computer or smartphone that's in this room is a physical version of a Turing machine. All Turing machines, even if, on the surface they may be different, they all have a few things in common. What are the basic functional elements of a Turing machine? What do all Turing machines do? Got a lot of computer scientists in the class.
It can read, write, erase, and move the tape.
It can read, write, erase any symbols that it sees on the tape, and then it can either move the tape or it can move itself along the tape, right? One element missing. It can read, write, erase, move itself.
Terminate?
Possibly. It has internal state. It can remember, right? So there's a soul. There's an internal part to a Turing machine. Again, this is just my jotting down the basics of it. But if you look at a Turing machine, it has the basics of also a robot. A robot has input. It has sensors. The Turing machine can move, or it can move itself, or it can move the tape. So the Turing machine can act on its environment. In this case, it's a very simple environment. It's just a piece of tape. And then it performs actions. Whatever actions it takes is a function of its input, or in our case, a robot, what it would sense, and any internal state, what it remembers. Right? Input, output, internal processing or internal state, and action, movement. Okay, let's move on. Let's move forward 20 years to 1956, and we're going to just go down the road to Dartmouth College. Back in the spring of 1956, a bunch of professors got together and they wrote a proposal to the government. And this is an excerpt from the proposal. We proposed that a 2-month, 10-man study, this is the 50s, so it was men, not people, 10-man study of artificial intelligence be carried out during the summer of 1956. That statement of artificial intelligence was the first use of that term. They made it up at this time to refer to what they wanted to do. So they proposed to the government to spend the summer of 1956 at Dartmouth studying AI. The study over the summer is going to proceed based on the following conjecture. This was not a proof, it was a conjecture that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. Note here they're talking about the assumption that it can be precisely described. When we talk about the building blocks of intelligence, planning, thinking, pattern recognition, adaptive behavior. These are all very vague terms. Can we take those vague terms and sharpen them into a very precise description? If we can make that description precise enough, we should be able to turn it into code and drop it inside a machine. And that machine should then be able to simulate planning, pattern recognition, adaptive behavior, recognizing language, producing language, and so on. Whatever the building blocks you believe are the building blocks of intelligence, we should be able to precisely describe them and then code them and build them. It's a conjecture that we can do so. An attempt will be made to find how to do this, how to make machines use language, form abstractions and concepts, solve kinds of problems that are now only reserved for humans. Oh, and also, by the way, we will get them to improve themselves. Rather than us writing a new version of code for the machine to make it smarter, the machine will make itself smarter. We think that a significant advance can be made in one or more of these problems if a carefully selected group of scientists, you know who that group of scientists is supposed to be, the group of scientists that's writing this proposal, give us money, we'll get together for the summer, and we'll work on this, and we'll make significant progress in AI over the summer of 1956. How did they do?
They discovered there's a lot more to it.
That's what they discovered. Should take us about a summer to figure out AI, right? How many years are we into this now? Over 50, 60 years, still going. For the vast majority of that time, for the vast majority of the last 50 years, little to no progress has been made on any of these building blocks of intelligence, with the exception of the last 10 years. Interesting. It's a very interesting time to be working in AI. For the history buffs among you, I just listed the actual attendees of the conference. Just for curiosity, do you recognize any names on this list?
McCarthy.
Yeah, John McCarthy. Do you know why? Just sounds familiar.
I mean, I've heard of the politician McCarthy.
He is not the politician McCarthy, but that's a good point.
Shannon is Shannon's love.
Okay, so for the mathematicians among you, you should know this name. We live in the information age. What is information? There's another very vague term, or it was a very vague term, until Claude Shannon came along, wrote a master's thesis, and defined exactly what information is. Alan Turing and Claude Shannon together, you can sort of view these as the two founding fathers of the information age, or the AI age. Very, very important player in AI and computer science in general. John McCarthy actually was the leader of the group. He's the one that actually coined the term artificial intelligence. Marvin Minsky, the second name on this list, he was the co-founder of the MIT AI lab. This is Mecca for anyone interested in AI. Next time you're in Boston, go to Cambridge, go to MIT, and there is now the CSAIL building, CSAIL, which is the Computer Science AI Laboratory. It's a beautiful building. You can go and walk through the public space on the ground floor. That was founded at about this time, and Minsky was the first director of that AI lab and was a significant player in AI for its first 30 years. Herbert Simon, interestingly, was an economist, kind of an interesting player in AI. Another important building block of AI is decision making. Economists are also interested in decision making. Won a Nobel Prize for his work in this area and contributed a lot to AI. If you've ever taken a class here with Professor Skalka, Professor Skalka was Herbert Simon's last graduate student before retirement. So it's all in the family here. Okay, some other names for you to research if you're interested. So that's 1956. Let's just take a pause for a moment. Like was mentioned in this founding document of AI, there are some certain goals of AI researchers. Most of us want to try and take inspiration from nature in some way. So we want to try and understand biological systems. What makes a robot intelligent? Here's a robot that's maybe not that intelligent, but it is performing one building block of intelligence, which is moving toward a useful signal, which in this case is light. This robot is performing what's known as phototaxis, moving towards light. Photophobia, as the name implies, is to move away from light. So we know lots of animals that run towards light sources. If you live in student housing and you go in the kitchen and you turn on lights in the morning, sometime you'll see those other organisms that dislike light and will run away from it, otherwise known as cockroaches. Cockroaches and other insects that exhibit photophobia or phototaxis, relatively simple. Maybe we can understand how they perform these relatively simple behaviors and build them into machines. Maybe once we figure out that, we can start to layer more and more interesting and complex behavior on top. It's a very different approach from the AI founding fathers who said, let's go after human cognition first, forming abstract concepts, solving mathematical proofs, understanding and generating language. Those were the original targets of AI. Since then, we've sort of tried to be a little bit more humble. Let's try and understand simple animal behavior first, build that into machines, move on to the next task, and so on. So, can we understand biological systems? Can we precisely describe them in mathematics, that we can abstract away the biological details and just get at the underlying algorithm? And if we do, then we can maybe drop it into machines. That's sort of the general approach in bio-inspired AI. Okay, let's move forward to the 1960s. There were a lot of interesting projects along the way, some that were more successful than others. This is the Eliza project, the first robot psychotherapist. So you sat down at a terminal and it would say to you, how are you feeling today? And you would type in how you were feeling. I feel terrible today. And it would say, why do you feel so terrible? And I'd say, because it's unceasingly cold, it would be nice to get some sunshine, and so on and so forth. And I'd have a nice conversation with Eliza. A lot of people that interacted with Eliza spent hours and hours talking to Eliza, even after long realizing that they weren't talking to a person, they were talking to a machine. We now have internet chatbots, which are supercharged Eliza bots. The original Eliza was very, very simple. It was made up of a whole bunch of if, then, else statements. So if Eliza received as input a series of tokens, pronoun, verb, proper noun, I, verb, proper noun, Eliza could create a response by pulling tokens out of that sentence and moving them around in different orders. Why do you, verb, proper noun? I feel terrible. Why do you feel terrible? Pretty simple, right? There were hundreds or thousands of these if-then-else statements, and you could get a more or less interesting conversation out of Eliza, but she would make some obvious mistakes that would immediately twig people to the fact that they were talking to a machine rather than a person. Okay, that's Eliza. This brings us to the Turing Test. Turing is famous for lots of things, Turing machines, but also the Turing Test. Eliza fails the Turing Test because a human that's talking to Eliza very quickly recognizes this is not a person. Most internet chatbots today, even the most sophisticated ones, still fail the Turing Test. Here's a video clip from a movie of someone or something undergoing the Turing test.
Just please don't move. Oh, sorry.
What movie is this clip taken from? Blade Runner. Okay. Again, required reading, or in this case, required watching for all students of AI. This poor fellow here is undergoing a Turing test, and spoiler alert, doesn't go very well for the interrogator in this case. I'll let you watch the rest of this at your leisure. Turing proposed that it's impossible to precisely define intelligence. This goes against what the founding fathers said in 1956. It's impossible to define intelligence. Everybody has a different definition. Get together with some of the students in this class together and see if you can come up with a definition. It is notoriously difficult. In previous years, we've done that in class. It runs out the entire time of the class, and it's hard to move on to other topics. So we're not going to do that today. Turing said, forget about definitions. I know that you're all intelligent because when I ask you a question, I usually get back an intelligent response. If you ask me to precisely define what I mean by that, I can't. So far, all of you have passed my Turing test, so far. We apply it to other humans. That's the test that we already use. Why would we not use it for machines? So a machine will be defined as being intelligent when it passes the Turing test. No machine has passed the Turing test yet. Will a machine ever pass the Turing test? Again, an open question. Okay, let's move forward to the 1980s now. This is John Searle, a philosopher. And Searle mounted a philosophical argument against the Turing test. And this argument goes as follows. If I can create a counterexample, if I can propose to you a system that passes the Turing test, but is obviously not intelligent, then the Turing test is not a good measure of intelligence, right? Okay, here's the system. Again, it's a thought experiment. This is known as the Chinese room experiment. As you see in the cartoon here, we have 3 people. The person in the room does not understand Chinese. They understand English. The 2 people outside understand Chinese. Doesn't matter whether they understand English or not. The Chinese speakers outside the room, they write a question in Mandarin, in Chinese, and they pass that piece of paper with the Chinese question on it through the slot in the door, and it's received by the person on the inside who does not speak Chinese. All they see is a bunch of weird symbols written on a piece of paper. They take the first symbol and they go to this huge book that they see in front of them. This book is written in English, which the person inside the Chinese room understands. And this book says, if you see this symbol, write on a new piece of paper these 2 or 3 symbols. Then if you see this symbol, write these symbols. So the book is not unlike the Eliza machine. It's a huge set of if-else statements, or you can think about it as a huge mathematical translation. The book is clearly not intelligent. It's an inanimate object. It's just a bunch of rules. If that book is large enough, then no matter what question is passed in through the door, the person inside should be able to use that book to compose a response, pass that response back out of the slot, and the readers on the outside of the room read the response and say, that's a very wise, reasoned, and intelligent answer to my question. Who passed the Turing test in this system?
The book.
The book, but the book's an inanimate object. That seems odd.
Not if it's an infinite, reality-defining book that can answer any question.
Possibly. Maybe it's not perfect, right? We're not perfect either. Let's assume it's not infinite. It's big, but not infinite.
What about the person who wrote the book?
What about the person that wrote the book? Aha, they passed the Turing test because they wrote the book. They must be intelligent, right? What's going on in the head of the person that wrote the book?
Also, all the reasoning is being done by the person in the room who we can assume is intelligent.
We can.
Well, it's just a language difference.
Yeah, it's just so the person sitting in the room, that's a human, right? Humans are intelligent, we know that. So there's something in the room that's intelligent. So that sort of invalidates Searle's argument. But Searle, if he were here, would say, we're not using the intelligent part of the human. That human in there is just a machine. All they're doing is looking up the symbol on the paper, flipping through the book, looking for that symbol, and writing whatever symbols they're being told to.
So
They're an automaton, they're not thinking themselves.
is he answering their questions, or is he just writing what they say in English?
Is he answering their questions? That is a good question. Who is answering the questions coming from people outside the room?
The room itself.
The room itself, right? The book, is it answering the questions? It's definitely not the human in the room. That person is just blindly doing what they're being told to do. They're not thinking about the question. They don't even know what the question is. So the room passed the Turing test, which seems odd. You can argue, as someone just did, it's the book that passed the Turing test, which seems odd. That's an inanimate object.
That object doesn't exist, so that's a hypothetical representation of a machine that passed the Turing test.
Exactly. It's hypothetical. And as you can imagine, the Chinese room is meant to be a metaphor for a Turing machine, right? A Turing machine receives symbols. It has a tape, which is the book, It erases those symbols and replaces them with new ones. So what exactly is Searle trying to argue here? That a machine can pass the Turing test? Seems odd.
I'm a little confused because I get that it's a hypothetical situation, but a book like that theoretically wouldn't be able to exist, right?
A book like that wouldn't theoretically be able to exist. So that's a good question. You mentioned you're confused. That's okay. That's the point. We should all be confused here. Clearly something is passing the Turing test in this case. People tend to disagree about what exactly is passing the test, right? So the book, can it actually exist? Another way as a computer scientist you can turn this around is, how big does the book have to be to fool 90% of Chinese people outside the room 90% of the time? Finite, infinite?
I guess this isn't exactly answering your question, but is the reason that the book, like, it passes the test, but it's like finite, that it's not modifying itself,
It's not modifying itself, it's just finite for the moment. Yep.
So like if you thought about intelligence, it's like, oh, I can, change my answer, and like if you gave it the same set of language every time, it would return the same way.
That's a good point. So in this description so far, there's no internal state. If you put the same symbol back in, if the people outside the room asked exactly the same question again, they'll get exactly the same answer back out of the room.
I mean, couldn't you just make this? Isn't it just like a hash map? And then couldn't you just test it and see if it actually works?
You could, right? Again, it's hypothetical. Let's stick with the internal processing part for a moment. We could add something to the book to say, if this symbol was seen in the last 10 minutes, put this symbol instead. We could add some internal state to the book.
But if you reference past conversations enough, eventually the book will break because it has no memory.
Exactly, the book will break after a while. Whatever you put in this room, assuming it's finite, it's not going to be perfect. How many of us are perfect conversationalists? If you come to my office hours and I know that I knew your name last week, I may not be able to call it up. I'm not perfect. I'm assuming not all of you are perfect. I don't want to try and convince you of any one conclusion from the Chinese room. People draw different conclusions from the Chinese room. My personal conclusion from this is that you have a non-thinking system, an inanimate object, the book, and a human, but you're not using the part of the human that you think is intelligent. The inanimate object is able to pass the Turing test. Not perfect. It doesn't fool 100% of the people 100% of the time, but it could probably do pretty well with a big enough book, right? So if that's true, that doesn't just militate against our understanding of the Turing test, it militates against our understanding of other words related to intelligence. The Chinese room is thinking. You put a question in, and you get an intelligent response back. It must have thought about the question and come up with or formulated an answer. How can an inanimate object, which is this room, think about a question and answer it? How can an inanimate object like this thing think about a question and answer it? Seems surprising. What do we mean by thinking? If I ask you a question and you give me back an intelligent answer, I conclude you must have thought about it. That was a bright response. What exactly was going on in your head when you thought about my question and gave me back an intelligent response? Were you doing something different than this?
Not really, you're retrieving past information.
This is one of the depending on how you view it, depressing or exciting conclusions of the Chinese room. That's what our brains are, is one big Chinese room. There is no homunculus. There is no little man or woman inside your brain that is thinking about the answer and giving it back. If there were, that's the homunculus response. There's a problem with the homunculus response. What is it?
You can just infinitely extrapolate it, like who's inside that person.
It's homunculi all the way down. There's a little man or woman inside the little man or woman who's thinking about how to get that person in, right? If you say, I'm doing something other than the Chinese room, the thing inside me is thinking about it and giving back a response. Unlike the Chinese room, you expose yourself to the infinite regress problem. What's inside that little man or woman that's doing the thinking for you. Again, I'm not trying to convince you that you're just an unthinking automaton. I want you to leave today's lecture feeling uncomfortable. You know that you think. Are you so sure? All right, that's the point of the Chinese room. All right, let's jump back out of philosophy, back into robotics, and back into the 1980s in this case. We're going to start our discussion of robotics with vehicles. Valentino Breitenberg was a neurophysiologist. He studied the physiology of brains of fruit flies. So if there was a piece of rotting fruit in the back corner of the room, and I opened up a glass vial of fruit flies, they would fly towards the rotting fruit and eventually find it and be very happy. In the 1970s, there were a lot of theories about how fruit flies actually did this. Most of those theories said fruit flies did something like differential calculus. They were following and computing gradients in space-time and following that gradient of smell of rotting fruit, and they were flying up the gradient towards the rotting fruit. At the same time, Professor Breitenberg was dissecting the brains of fruit flies. You've probably seen a fruit fly. They're very, very small. Imagine the brain of a fruit fly. Imagine trying to dissect the brain of a fruit fly. Not so easy to do. Breitenberg said there is no way that these things are performing differential calculus. It's impossible. So he wrote this book, which if you read it, it reads like a fairy tale. Chapter 1 starts by saying, once upon a time, there was a simple thing called Vehicle 1. Vehicle 1 had a body. It had a wheel or a flipper, doesn't really matter for our purposes, and it has a single sensor on the front of it. Imagine, and that sensor is attached to the wheel. Imagine now what you would think if you saw Vehicle 1 swimming around in a pond. It's restless, you would say, and does not like warm water. Why would we say that? If we have a sensor on the front and that sensor is a temperature sensor, then the warmer the temperature, the more that sensor fires, sends the signal along the synapse, the wire that's connecting the sensor to the motor, and the faster the wheel turns. So you'd say it does not like warm water because it will drive faster through warm water, but it's quite stupid because it's not able to turn back to the nice cold spot that it overshot in its restlessness. So when this robot comes into cold water, it will slow down because the cold water will cause the temperature sensor to fire at a lower rate, which will send a signal to the wheel and cause the wheel to spin slower, but it's slowing down. It'll leave the cold spot and enter another warm spot, at which time it will speed up, right? It missed the cold spot, never turns around, it goes back to the nice cold spot that it likes. Anyways, it may be stupid, but you'd say it's probably alive because you've never seen a piece of dead matter move around quite like that. Why would a very serious scientist, a neurophysiologist, write a fairy tale about vehicles and use this very non-scientific language? Is Vehicle 1 restless? Does it dislike warm spots and like cold spots? Obviously not. That's ridiculous, right? Okay. Let's move on to Chapter 2. And in Chapter 2, we have two different robots, 2A and 2B. This is Vehicle 2A, the aggressor. In this case, we're back on land now. We have our robot in the far right, and we have a light source here. Let's imagine that light source is a flashlight, and we're going to come at this vehicle from the front left. A few minutes ago, I just showed you a Lego robot, which is exactly Vehicle 2A. It's got two light sensors on the front of it. Left sensor is attached to the right wheel, and the right sensor is attached to the left wheel. These are known as contralateral connections, contra across, lateral side. So we have synapses that are crossing the side of the robot and connecting one sensor with the other side of the body, contralateral connections. Why does this robot turn towards the light?
The sensor on the left detects more light, so the motor on the right spins faster.
Exactly. So it turns towards the light. Once it makes a small turn towards the light, what happens at the next time instant?
Be more balanced if it's more equivalent light on the two sensors.
Exactly. So it's turned a little bit towards the light, which means the difference in light intensity falling on the two sensors has equalized a little bit more. What does that mean for the behavior of the robot?
Turn less sharply.
It'll turn less sharply, so it'll start to even out its curve and start to head towards the light. What else can you tell me about the behavior of the robot, given what I've told you about its insides so far? It turns towards the light and straightens out. What else happens?
It moves towards the light.
It'll move towards the light, moves a little bit towards the light, and then what happens?
It'll speed up.
It'll speed up. It moves towards the light, so the total amount of light falling on the two sensors speeds up. It will speed up, and if it's a naked bulb, it will smash into it and destroy it. This is the aggressor. If you put any naked light bulbs anywhere near it, it will destroy them. It hates lights with a passion, right? You're laughing. Why are you laughing? Does the aggressor hate? Is vehicle 1 restless? It's ridiculous, right? We love, we hate, we get restless. We're different from Bradenburg's vehicles, right? Think on that. We will come back to that on Tuesday. You have a quiz due tonight, and we will talk about assignment 2 next Tuesday morning. Thanks very much.